there are some applications, but I will tell you this one first. Well, only this one in this lecture. The basic idea is, basic question we were trying to ask, and unfortunately we still don't have a very good answer because there are many computational limitations and how to handle the so-called big data, well, there are many challenges we are still working on. But the overall question is, look, if I want to know your pulmonary function, how well your lung is, then somehow you need to go to the hospital and do this spirometry and so on. And the very natural question is, can we replace this spirometer, which is a very bulky machine, as big as this one, and you sit in front of it, woo, and so on. If you ever done it, then you know what it is. Not very fun, and you cannot carry this very bulky device with you at home and take it home and do it every time. No, it doesn't. It's not practical. So one question is, can you use any simple devices so that you can collect the pulmonary function? Okay, so that you can collect pulmonary function. For example, right now there are many devices like you wear a clothes, and on the clothes is very tight, covering your body, but there will be some sensor on your chest and sensor on your abdomen, so that when you are breathing, remember when you are breathing, your chest is expanding and your abdomen is also expanding. So there will be some kind of movement of your chest and abdomen that tells you how you breathe. Okay, and can we use this information to help us achieve some analysis of pulmonary function? That will be the basic question we try to ask. And why is it possible? A very quick 1-minute physiology that is very ideal situation is when your chest expand, the chest band movement will kind of provide information of cross-section volume of your lung. And when your abdomen move, it will tell you how your longitudinal axis expand when you breathe. So somehow, by combining the magnitude of your chest band and your abdominal band, you get somehow the volume of your lung. And the volume of your lung changes actually gives you how you breathe. In particular, how fast you breathe, how slow you breathe. So the basic idea is leveraging this information and ask if we can recover your flow signal, your airflow signal. That will be the kind of signal processing mission. Okay, and this is not really a new question. In anesthesia, back in 2010, even 2005, people have considered several ideas using linear regression, take different channels and truncate into pieces, and just run some linear regressions and so on, or run blah blah blah, machine learning, right? And nowadays, I believe people use deep learning and so on, blah blah blah. Okay, and we were thinking, look, based on everything I have told you, actually, the oscillatory signal, in particular, respiratory signal, its morphology actually encodes a lot of information. In particular, in breathing, it encodes how fast you inhale, you exhale, and inhale, exhale, what is the timing, and so on. All the information encodes your lung function. So we want to use this so that we are able to design some algorithms. So to leverage the time-varying wave-shape function, we just apply Synchrosqueezing transform, as I told you, to get time-frequency representation. And from time-frequency representation, I run some time-varying bandpass filter to extract each oscillatory component. Once I get each oscillatory component, I say, hey, now, once I get all of them, we can design features. You have amplitude magnitude modulation, you have the phases. And here I put sine and cosine because by combining sine and cosine via trigonometric identity, you can get a global phase shift. Okay, so that by combining that, at time tj, at the jth sampling time, you get the features from the ABD urothoracic movement or abdominal movement. We leverage this guy as a feature. As a feature. You can consider other features, no problem. But we found this feature to be useful. And again, how to get this feature? You use Synchrosqueezing transform, I mentioned. Use the reconstruction, ridge extraction, then use reconstruction formula. And now you get features. Okay? So, what will be the mission? The mission is asking, hey, look, I now have THO and ABD, or AND, okay? How can we recover the airflow signal so that we can better understand your lung function? Okay, so what we do is, well, we have a set of data you all know very well, like a regression. This is labeled. You have xi, which is the features from ABD THO. You have yi is your airflow signal. And we just want to use this label data to learn the relationship in between x and y so that we can apply to the unlabeled data when the subject only has ABD and THO signal, and to see how accurately we can achieve. Okay, that's the motivation. Now, coming to mathematics, coming to statistics, it is just a regression model. We have ABD and THO. You can, by your eyes, see, well, look, there's some relationship in between them, right? It's not totally random. And let's assume this relationship is satisfied by this function f, which encodes the nonlinear relationship in between your chest movement, abdominal movement, and airflow. But what is it? We don't know. We want to learn it. Okay? And we assume it's not linear. And traditionally, as I told you, people used different designs of X and use maybe linear F or quadratic F, some quadratic regression or something, where people consider several things. Okay, and we just assume, well, here you see something very simple. We just assume, yeah, there is some IID normal error, and you can imagine why, because we want to use very kind of a simple Bayesian approach, Gaussian process regression. Okay, so this is the model. And then, I bet most of you know better than me about Bayesian, otherwise we will not be here. But I'll just quickly give you a 1-minute recall of Gaussian process regression. And then later on, there will be instructors tell you more details about how to carry over the computational details and how to achieve the estimation of every single step. But the basic idea is very, very simple. You have a function, suppose it's continuous, then you can do discretization. Okay, so you generate an m-dimensional vector. Very simple, clean data. And now you have noisy data. This is noisy observation called xi, which is the features we design. Now we want to predict f of xi, where xi is in something that is unlabeled. So you can just put a prior, just like Steve told you yesterday, and the prior is very simple, just I say Gaussian. But here, there is a very important thing to say. You need to design these coefficients very, very carefully. And this coefficient is the chosen covariance function. You choose a priori, called C, and you just put sigma ff in. We'll talk about how to design the covariance function C later, because that will link us back to spatial statistics or manifold learning. That will be the second part of this this lecture. Okay? And then once you have this part, you can say, oh, okay, you have the unlabeled data F star that we want to estimate, and then you can generate a large covariance matrix coming from all the covariates from the labeled and unlabeled data. So this is n plus n. This is n plus n by n plus n matrix, and everything can be calculated precisely using the covariance function C. Then you can calculate the Gaussian prior as a sigma star, sigma tilde. That is, you have a joint distribution of the noisy data and the unlabeled data. That is what you get. And the posterior distribution, like Steve told you, just do some calculation, you get this guy. And you can use this guy to calculate the distribution or estimation of whatever you want. And then for details, for example, how to estimate sigma square noise, usually it's the maximum likelihood approach and so on. And I think details will be covered by the later lecture instructors. Okay. And then, once you get this part, 1 minute, right? I'm not lying. Then what you can do is, I say, hey, I now want to choose the covariance function. But how to choose the covariance function? Turns out there is a very interesting observation. That is, the coefficients actually in between the amplitude and the phases of ABD and THO, they cannot be random. They are very high dimensional space. You see it's 24 dimensional. And actually in practice, we'll use the lag map to embed the signal into higher dimensional space, like 240. It's a very high dimensional space. And you don't want to work with very, very high dimensional space. And then you see that actually that high dimensional space, all the data are related in some nonlinear way. But what will be that nonlinear way? We just make a further assumption, which actually you can write down details if you like. It is actually a manifold. There is a nonlinear manifold that parameterizes all the possible coefficients, covariance. And this is the starting point of introducing manifold learning to time series analysis. And if it is really a manifold, and you had some ideas about, you learned what manifold is, then I don't need to mention too much. But if you have no idea what manifold is, no need to panic. Manifold is just like, this is a paper, right? Isn't this flat? Okay, this is a two-dimensional manifold, flat, which is like a fine space in three-dimensional space. Now, I can curve it, right? So you see, this is no longer an affine space. This is a manifold. So there is some nonlinearity. But there's a very important property if you pay attention. You see, if you are a very, very tiny nanometer size creature living in this point, what do you think? Can you see the curvature? No, right? It's just like us. We live on the Earth. If we look around, actually the Earth looks like flat. And that puzzled people for how many centuries? Longer than 20 centuries, right? Similar scenario. And then you can even do something more complicated. You can put things together in this way. Oh shit, this is not. Right? You can generate something like that. And this is a cylinder. It has topology. It has topology. Okay, it is no longer like flat or can be parameterized by just one chart. Okay, so you don't need to know the mathematics behind it. You just need to know the basic idea is we want to quantify some relationships in between coefficients that is nonlinearly related. But this nonlinearity is not crazy. Locally, it behaves like linear. And it can be approximated by something of higher order, which is called curvature. Okay, so this is another 1 minute introduction of manifold. But we found that, hey, there is really a manifold, and there are some even topologies. So if we do not respect it, we found that the desired covariance function will kill you, give you very, very erroneous results. So we need to respect the manifold. So what we did was very simple. We just say that, hey, here we want to design the covariance function. And I will tell you in a bit that if you choose the covariance function, which needs to be what? Positive definite, right? Needs to be symmetric, right? If we choose it to be the hit kernel on the manifold, then things become better. You respect the geometry, you can get some better estimation. Okay, and this is the result. Okay, you can see, for example, this is a very good case, and then you estimate posterior, the median will give you, okay, well, it's too small, but you can see that the black one and the red one are too close. It's the problem too close, right? You can see the ground truth and the estimator. They're very close, and you can see a 95% credential interval. I mean, they cover very well. This is an okay case, and this is a very bad case. And actually, you can see that the 95% credential interval, the bad case, doesn't really always cover the ground truth. So this is a very, very challenging case. And you can apply it to sleep. When you are sleeping, I just want to use your chest pad to estimate your respiratory signal, and this is the overall accuracy. And you can see that if we consider the benchmark linear regression model, the result is order beta, much better, which suggests again the existence of nonlinear structure inside. Okay, this is the ultimate goal, but still working on it. It's very slowly moving. We want to really get this volume flow plot so that we can do more diagnosis, but it is kind of challenging for many reasons. Okay, very good. So this is another plot, just try to show you if you do not respect the geometry, but just use the traditional Gaussian process regression. This is a ground truth, this is the estimator, and you can see quite a lot of errors compared with the ground truth. Okay, and this is the estimator using those subsample data set respecting the manifold structure. Okay, just in case you are curious, what is this data? This is actually the temperature data recorded from your hand. And this is a patient with renal disease. Okay, and we want to say that suppose we can only sample some small points, temperature on the finger, on the hand. Can we get to the overall distribution, overall behavior of the temperature on the hand? That's the overall goal. Okay, so you can easily get a very, very dense sample set on the hand, right? But to get the temperature is a sensing process, which is like expert's label. That is expensive. So usually we can only get some points. In particular, if we want to achieve high frequency sampling. Long-term monitoring. Okay, so that is the tool that can help you to achieve a high quality estimation. But if you look at this guy, our hand is actually a surface. And surface is what? It is a two-dimensional manifold. Okay, so you want to respect the two-dimensional manifold structure. That is the key information. This is another similar example, but I will skip it. Okay, so let me tell you some stories about graph model and manifold learning, and what do I mean by using the hit kernel? How can you construct a hit kernel, and in what sense? Okay, so what is a graph model? It may sound a bit jumpy, but think about it. I talk about time series so far all the time. But at one moment, I suddenly told you, I get a signal, I decompose it into several harmonics. I convert it into what? Into high-dimensional time series, isn't it? And high-dimensional time series, in the end, will give you many, many points for example, B1 hat Tj, right? B4 hat Tj, and you have sine, you have cosine, da da da. So, right, this is in 24-dimensional space. This is x Tj. Right, so somehow I have a signal f of t, which is in one-dimensional space. I convert it into a high-dimensional time series. This is a high-dimensional stuff. And I say that not only so, this is actually on a manifold embedded in 224. And even further, I can do length map and so on, whatever techniques you like. But don't worry, we just get something on a manifold. But you have several points. And there are some kind of dynamics on it. Okay? That's a conversion. And why so? Because each piece of information encodes separate information, different information. It's just like a resonance chamber. Resonance chamber, depending on the morphology, the shape of the chamber, you have some resonance. And the resonance, different frequencies and different components play different roles, echoing, reflecting the behavior of the chamber. Okay, so we get the feature. And now we get high-dimensional data. Now I want to tell you, if you have high-dimensional data, and it is really living on a manifold, how to do the analysis. We will not go into stochastic differential equation because I don't have time, but the logicity, theorems, Paris recurrence, everything, they are very interesting topics that will come into play. Okay, in this setup, but I will not go there. Oh, right, I haven't talked about this. Okay, once we have high-dimensional data, what to do? Usually we construct a graph. And what is a graph? A graph consists of several components. The first one is endpoint, that is vertices. The second one will be all the edges connecting data points. The third component will be some weights on the edges. Okay, so this is a very typical example. You have graphs, vertices, and there are some edges. Over each edge, you have some affinity. And we call the graph to be undirected if the weights are symmetric. It can be more complicated, like you can discuss directed graph or something, but let's forget about those complexities. Okay, so this is a graph. And this is something you can see very, very commonly. You have some nodes, right, and they are connected in this way, blah, blah, blah. This is a directed graph. And you can see this graph everywhere. Social networks, economic networks, right, medical networks, there are several things. You see these plots everywhere in nature science papers, right? And well, graph is everywhere. But usually we may only have a set of high-dimensional points. Then how do you construct a graph? If I just give you, like your collaborator just give you a set of high-dimensional vectors, not anything more, then what you need to do, if you want to consider graph model, then you need to construct the missing parts. For example, what will be the edges, and what will be the affinity on it. So usually you can consider either complete graph, connect every pairs, or consider KNN, k-nearest neighbors policy. But then you need to have a notion called metric, how to compare 2 points. What will be the metric? What will be the distance between 2 points? Or you need to consider epsilon ball. There are several policies you can use to construct graphs. Once you construct graphs, you can just assign some affinities. For example, you can use Gaussian affinity. What does it say? If 2 points are very far away, distance is large, then affinity will be low. But if the 2 points are very, very close, then the affinity will be high. And how far is far, how close is close, usually that can be controlled or adapted by the bandwidth edge. Okay, so that in the end, you get a graph, an affinity graph. But how to choose bandwidth? Actually, this is very, very important, and we will not go there. But usually the idea is you choose some kind of percentile of pairwise distances, and you can show that even when noise exists, and the noise is high-dimensional noise, this percentile is robust to recovering the information. That is kind of something, if you have interest, I can provide some literatures. But how to choose the bandwidth is very, very critical. If you choose the bandwidth wrongly, you can get paper published in Nature and Science. Okay. Okay, so you didn't know what I meant. Okay, very good. Okay, so affinity and transition matrices. Okay, and now what you do is you can construct an affinity matrix from the affinity graph. So you just build up an n by n matrix, and you say that the ij entry will be the wij if ij is an h, otherwise 0. And you construct a diagonal matrix by summing all the rows of W matrix. And then you just consider transition matrix D inverse W. And if you think about it, what are you having here? The W matrix is a non-negative matrix. Non-negative matrix is not non-negative definite matrix. They are different. Non-negative matrix only means all the entries are non-negative, which doesn't mean that it is non-negative definite. And we can have used Faulkner's theory to show that if it is Gaussian, then it is non-negative definite. But forget about all these technical details. But after you get it, D is certainly positive, non-negative. So the D inverse W is also non-negative. But all the entries, all the rows will be summed up to 1, right? So each row will tell you what? Each row will tell you how you jump from one point to another. This guy is density major. So it tells you a way to do random work on the graph. D inverse W, D inverse W is a random work on the graph. And the random work is determined by the affinity graph, how points are related. Now, we can consider an algorithm based on graph model called diffusion map. This diffusion map is very simple. Remember, I told you D inverse W is a random work. What is random work in the continuous setup? It's like diffusion, right? It's diffusion. So you are doing the diffusion on the graph. So what you see is, hey, this is really a random work on the graph. So how about if we try to estimate its metastatus? Use the metastatus, then we can use the metastatus to define a map called diffusion map. And what is the meaning of that one? What is the meaning? Before the meaning, the first question you may want to ask is, why do you have an eigendecomposition? If you think about it. Because D inverse W is not symmetric, isn't it? If it's not symmetric, how can you get eigendecomposition? Okay, so this is several mathematical details. I will not go through all of them, but you can do it as homework. I can give you, by similarity, you can show that you get eigendecomposition guaranteed. Once you have eigendecomposition, I in particular, the left one, right one, it tells you, it describes the stability of the status, the random work, the diffusion on the graph. So you can use it and view it as the status of each point, and you achieve the embedding by leveraging the eigenvalues and the eigenvectors. Okay, this is called diffusion map. And this diffusion map actually can be applied to visualize high-dimensional data or dimension reduction, and in particular to recover the nonlinear geometry. And there has been a series of work so far, and well, there are some new current works, but anyways, it tells you quite a lot of information. And furthermore, you have Vi, Vti, Vtj. If you evaluate the Euclidean distance in between this point, that is called diffusion distance. And diffusion distance actually gives you a very nice interpretation geometrically. In what sense? If you look at all these points, you see this is like a dumbbell, right? Many points here, a very small isthmus, and another point. Now there are 3 points, A, B, and C. Now I ask you to compare the distance in between A and the B, and the B and the C. What will you say? If you use Euclidean distance, you will say, hey, A and the B and C, their Euclidean distances are the same. But is it true? Not really, right? If you think about it, yes, Euclidean distances are the same. But just by looking at those points, their distance might not be the same. But if you think from a diffusion perspective, you want to diffuse from B to A. What do? You need to respect the geometry, right? You need to diffuse over a point, and if you're lucky enough, you enter the isthmus, then you can arrive A. But if you want to diffuse from B to C, actually there are many paths you can go from B to C. So diffusion helps you to determine the notion of distance by respecting the geometry. Okay, so by this diffusion, the differences is told, and you capture the true distance in the sense of what you can say better is geodesic distance on the nonlinear geometry setup. Okay, so this is a very kind of quick introduction of the graph model. Once you have a graph model, on the graph, if you assign some affinities, then what you can do is you can design some algorithms called diffusion map. With diffusion map, somehow you can better determine the notion or the distance in between points and so on. And there are a lot of details. If you have interest, you can dig into offline. It's a very interesting field. And now I want to tell you the story. Suppose you really have a manifold, and I have told you, well, diffusion distance helps you to describe or respect the distance information. Then how to get the covariance function designed using the heat kernel. The basic idea is actually very simple. In the following sense, remember I told you if you have a set of high-dimensional data, then you need to connect them, right? After connecting them, you construct a graph Laplacian. You construct an affinity graph, and from the affinity graph, you can construct a random walk on the graph. From the random walk, you can construct diffusion map. And the diffusion map comes from the eigendecomposition of graph Laplacian. Now, what is missing? The missing part is the manifold. How to take the manifold into account. Again, if you don't know what manifold is, just think about what I told you about this nonlinearity. There's not anything difficult. Everything locally is like linear, so you don't need to worry too much about it. Then, what you do is, okay, assume you have a d-dimensional, smooth, closed, and connected Riemannian manifold. And now, you have a random vector. This random vector is p-dimensional random vector. But you assume that the support of the range of this random vector, is on the manifold. And so that you can induce a major on the manifold. So let me make it clear so that we don't get confused. So what you have is x from omega fp to rp. So you assume that x, the range, is manifold in RP, such that you have some kind of induced major P on the manifold. And you assume that it is absolutely continuous to the Riemannian major on the manifold. Because this manifold is embedded, and I assume it's isometrically embedded, so that you can write by Radon-Nikodym is Px of x dVg. And this is the density function we have, which is defined on manifold. And we assume it's positive. Okay, so we made the assumption that you can sample everything over a manifold. That is, maybe better to write it this way. The mean of Px is positive, and then we assume Px is C4. Okay, and now you have this random vector, and you have this manifold. You know how to do the sampling. You have density function, so you just sample IID n points from this random vector. This is your data. So you now get n points independently from the manifold, which you have n high-dimensional points, so that you can construct a graph Laplacian from it. And the main theory I want to tell you is just one line. It tells you that by constructing graph Laplacian D inverse W, you have eigenvectors and eigenvalues. And from eigenvectors and eigenvalues, if you do some normalization, which you can ignore the detail, you can take the eigenvector, after normalization, you construct this guy, which is exponential minus eigenvalue and the eigenvector. Okay, and you take the top k eigenvectors, then the theory tells you that you can reconstruct the real heat kernel on the manifold with some uniform errors. And in this sense, you reconstruct the heat kernel. And this guy, as you can see, is obviously a positive definite matrix. Non-negative definite matrix. It has some degeneracies, so when you play with Gaussian process regression, you need to be careful a bit by considering reach and so on. Okay, there are some literatures. If you have interest, you can take a look. Okay, so that's what I said. In the end, what we did was, when we need to choose a covariance function, C, we just choose the heat kernel. We just choose the heat kernel. But we still have several troubles right now. For example, when data size is very large, for example, in my application, I can easily get 10 million points. How to run 10 million points with Gaussian process regression? I think this is also still challenging nowadays. And there are some ways that we can speed up things, but numerically not very stable. So this is still an open question that we need to resolve. So as an open question, I think this is maybe good, and I hope some experts from Bayesian society here would find this interesting, and can. I'm very happy to chat more offline about how to make it how to move things forward. Okay, the final slide I want to show you is, this is actually what I want to show. I always like to show, but because Long told me not to be too aggressive, so I decided not to tell you too aggressive stories, but only this story. Because you see some fields, people like to claim a lot, like everything can be solved by some kind of deep shit, right? And so, what is dimension reduction? Are you sure you can do dimension reduction? Are you sure? Are you sure you can achieve visualization? Are you sure? What do you really mean by that? Okay, and you all know Klein-Bartle, right? At least you hear about it. It is very simple. Klein-Bartle is something like that. You have a cylinder, right? And now imagine, use your mind. Imagine you can curve it. And if you link them together, what do you get? You get a torus, right? A donut torus. But now I tell you that when you bend it, connect it, I don't want you to connect it in this way. I want you to connect it, but in this way. In three-dimensional space, how can you achieve this without breaking the topology, without breaking the manifold? You cannot. But you can do it in four-dimensional space. If I give you one extra dimension, imagine you zero mind, then you can do this and bend it a bit and connect both ends in this way. And that's called Klein-Bartle. And this is a Klein-Bartle three-dimensional realization that you may see as a product in some souvenir store. Klein-Bartle. Okay, there are even some, I remember some mocha bottle, mocha coffee scenes with this formula. But no matter what, you know it's complicated. Now, suppose I claim, I tell you, trust me, diffusion map is great. It solves everything. You can visualize all the data. Good. This is Klein-Bartle. You use diffusion map. You just get something like, it's beautiful, isn't it? And how much do you trust me about seeing everything? How much do you believe me in seeing the ground truth? So, what I want to emphasize, and this is the last slide, is data analysis cannot break the topology constraint. Okay, so at least you need to know some basics before you claim a lot that you can solve or replace positions